Section 1: Paleoclimates. Digging deeper. How geologists find out about paleoclimates. Global climate. Climates differ from one region of Earth to another. The climate of a region depends on latitude, elevation, and geographic features. However, the entire Earth also has a climate. This is called global climate. It is usually expressed as the year-round average temperature of the entire surface of Earth. Average rainfall is also an important part of global climate. Today, the average temperature on the surface of Earth is about 60 degrees Fahrenheit, but Earth's climate has changed continually over geologic time due to a number of different causes. Direct records and proxies. In the Investigate, you use two different ways to learn about past climates. In Part A, you carried out an investigation of growth rings from a tree and saw how tree rings can be used to infer how climate may have changed from year to year over hundreds of years. In Part B, you investigated climate by using a model that represented the pollen in lake sediments. This digging deeper will help you to understand more about the ways in which scientists study past climatic conditions. A paleoclimate is a climate that existed sometime in the past. It could have been as recently as just a few centuries ago. On the other hand, it could have been as long as billions of years ago. During the Mesozoic era, dinosaurs roamed the Earth. This was 252 to 66 million years ago. Global climate was warmer than today. The Pleistocene epoch was 2.6 million to 10,000 years ago. This is when mastodons and cave people lived on Earth. Global temperatures seesawed back and forth. The climate went between cold glacial intervals and warmer interglacial intervals. During glacial intervals, huge sheets of glacial ice covered much of northern America. Just a few hundred years ago, the climate was about 3 degrees Fahrenheit cooler than it is now. The time period from about mid-1300s to mid-1800s is called the Little Ice Age because temperatures were generally much colder than today. Glaciers in many parts of the world expanded. Global temperatures have gradually increased since then, as Earth has been coming out of the Little Ice Age. Today, Earth has only two continental ice sheets. One covers most of Greenland, the other covers most of Antarctica. The last retreat of continental glaciers took place between approximately 20,000 years ago and 8,000 years ago. That was before the invention of writing. Therefore, there is no direct record of this change. Systematic records of local weather go back only about 200 years. These are made with the help of accurate weather instruments. A global network of weather stations has existed for an even shorter time. There are historical accounts for individual places. One of the most notable is China. For certain places in China, records extend back 2,000 years. These records are useful. However, more information is needed to understand the changes in climate. Paleoclimatologists use a variety of methods to infer past climate. Together, the evidence gives a picture of the history of Earth's climate. Unfortunately, nothing gives a direct reading of past temperature. However, many kinds of evidence give an indirect record of past temperature. These are called climate proxies. Something that represents something else indirectly is called a proxy. In some elections, a voter can choose another person to cast their vote and represent them. That vote is called a proxy. There are many proxies for past climate. However, none is perfect. Tree rings. In the Investigate, you examined how paleoclimate is recorded in the annual growth rings in trees. Trees grow more during warm years than during cold years. A drawback to tree rings is that few tree species live long enough to provide a look very far into the past. Bristlecone pines, which can live as long as 5,000 years, and giant sequoias, which can also live several thousand years, are most often used. Fossil pollen. Pollen consists of tiny particles that are produced in flowers to make seeds. Pollen is often preserved in the sediments of lakes or bogs. It is blown in by the wind. For example, a layer of sediment may contain a lot of pollen from spruce trees, which grow in cold climates. From that, you can infer that the climate around the lake was cold when that layer of sediment was being deposited. Geologists collect sediment from a succession of sediment layers. See Figure 2. They count the number of pollen grains from different plants in each layer. Then they make charts that give an idea of the climate changes that have taken place. Pollen is easy to study because there is so much of it. Geologists also study fossil plants and insects to reconstruct past climates. Ice cores. In recent years, ice cores have become a powerful technique for studying paleoclimate. Ice cores are samples removed from ice. Very long cores, about 10 centimeters or 4 inches in diameter, have been obtained from both the Greenland and Antarctic ice sheets. The longest, from Antarctica, is 3,623 meters, about 2.25 miles long. Ice cores have been retrieved from high mountain glaciers in South America and Asia. Glaciers consist of snow that accumulates each winter and does not melt entirely during the following summer. The snow is gradually compressed into ice as it is buried by later snow. The annual layers can be detected by slight changes in dust content. The long core from Antarctica provides a record of climate that goes back more than 400,000 years. Bubbles of air trapped in the ice contain samples of the atmosphere from the time when the snow fell. Paleoclimatologists study the oxygen in the water molecules in the ice. Almost all of the oxygen atoms in the atmosphere are in two forms. They are isotopes of oxygen. Isotopes are atoms of the same element. However, they have a different number of neutrons. Therefore, they have different masses. The two isotopes are oxygen 16, written 16O, and oxygen 18, written 18O. They are the same chemically, but they have slightly different masses. 18O has a greater mass than 16O. The proportion of these two isotopes in snow depends on average global temperatures. Snow that falls during periods of warmer global climate contains a greater proportion of 18 oxygen. Snow that falls during periods of colder global climate contains a smaller proportion of 18 oxygen. The ratio of 18 oxygen to 16 oxygen can be measured very precisely with special instruments. Another important way of using glacial ice to estimate global temperature is to measure the proportions of the two naturally occurring isotopes of hydrogen. These are 1H and 2H. 2H is called deuterium. The air bubbles in glacial ice contain carbon dioxide. The amount of carbon dioxide in the air bubbles depends on the amount of carbon dioxide in the air. This in turn can be linked to global temperatures. When the paleoclimate is thought to have been warm, the air bubbles in the ice core show higher levels of carbon dioxide. When the climate was cold, the levels of carbon dioxide are lower. Measurements of carbon dioxide taken from the cores give a global picture. This is because carbon dioxide is spread uniformly in the global atmosphere. A third component of the ice that yields clues to paleoclimates is dust. During colder climates, winds tend to be stronger. The stronger winds erode more dust. The dust is deposited in small quantities over large areas of Earth. Deep sea sediments, foraminifera, forams for short, are a kind of single-celled animal that lives in the ocean. Sand-sized shells of the forams build up in layers of ocean bottom sediment. During warm climates, the shells spiral in one direction. During cold climates, an interesting change in anatomy takes place. The shells spiral in the opposite direction. The shells consist of calcium carbonate. Calcium carbonate contains oxygen. Geologists can measure the proportions of the two oxygen isotopes to find out about paleoclimates. The shells have more 18O during colder climates. They have less during warmer climates. Note that this is opposite to the amount of 18O in the precipitation that falls and is stored in glacial ice during colder climates. Large amounts of 16O are stored in glacial ice during cold climates. Therefore, the 18O content of the oceans is somewhat higher. The shells of foraminifera obtain the oxygen for the calcium carbonate in their shells from the ocean. Therefore, in cold climates, they use greater amounts of 18O than 16O to build their shells. Glacial landforms and sediments. Glaciers leave recognizable evidence in the geological record. Glacial landforms are common in northern North America. Glaciers erode the rock beneath them as they move. They then carry the sediment and deposit it to form distinct landforms. Cape Cod in Massachusetts is an example of long ridges of sediment left by glaciers. Long Island in New York is another example. Scientists measure their ages using special techniques. Cosmic rays hitting the surface rocks in deposits split some of their atoms. This happens at a predictable rate and can be used like a clock to date the deposit. The Long Island deposit dates back from the last glacial maximum 22,000 years ago. After this time, the ice began to melt and the ice sheet covering North America began to retreat. Similar deposits are found as far as south as Missouri. As glaciers advance, they grind up the bedrock below them. Some debris is shoved ahead of the glacier in a gigantic ridge. Some of it gets washed out by streams. This sediment is very fine-grained and easily carried by the wind. The dust is carried far from its source. It is deposited over large areas as a sediment called loess. Some of it gets deposited on the surface of great ice sheets in Greenland and Antarctica. Higher concentrations of wind-blown dust in cores reveal several intervals of glaciation during the Pleistocene epoch. Glaciers also leave evidence in the ocean. When glaciers break off into the ocean, icebergs float out to sea. As the icebergs melt, glacial sediment in the iceberg settles down to the ocean bottom. This type of sediment is easily recognized. This is because it is much coarser than other ocean bottom sediment.